Imagine shining a light through two narrow slits. You'd expect to see two bright bands on a screen behind, right? That's common sense, everyday experience. But the double-slit experiment, a cornerstone of quantum mechanics, reveals a reality that defies our classical intuition. It plunges us into a world where light and matter behave in ways that seem impossible, where the act of observation alters the observed, and where the very fabric of reality appears to shimmer with uncertainty. This experiment, simple in its conception yet profound in its implications, has captivated physicists for over a century. It has forced us to re-examine our fundamental assumptions about the nature of light, matter, and the very act of measurement. In the heart of this experiment lies a mystery that continues to shape our understanding of the universe at its most fundamental level. The setup of the double-slit experiment is deceptively simple. A source emits a beam of light, or in later versions a stream of electrons or other particles. This beam is directed at a barrier with two closely spaced parallel slits. Behind the barrier lies a detection screen, ready to record where the light or particles land. This experiment can be performed with various types of particles, but let's stick with light for now. When light passes through the two slits, it doesn't behave as we might expect. Instead of creating two distinct bands of light on the screen, corresponding to the two slits, it forms an interference pattern, a series of alternating bright and dark bands. Classical physics, the physics of our everyday experience, offers a straightforward explanation for how particles should behave in this experiment. If light were composed of tiny, indivisible particles, like miniature marbles, we would expect them to pass through the slits in straight lines. Each particle would go through one slit or the other, and the particles would hit the screen in two distinct bands, directly behind the slits. This is analogous to rolling marbles through two doorways. You would find marbles clustered behind each door but not in between. However, the double-slit experiment reveals that light, and indeed all matter at the quantum level, doesn't quite follow these classical rules. Instead of two distinct bands, the experiment produces an interference pattern on the screen. This pattern is the hallmark of wave behavior. When waves, such as water waves, pass through two slits, they create an interference pattern because of the way they interact. Peaks and troughs can reinforce each other, creating bright bands, or cancel each other out, creating dark bands. The double-slit experiment demonstrates that light, even though we often think of it as a stream of particles, photons, also exhibits this wave-like behavior. Section 5. The Observer Effect, Watching Reality Change. Perhaps the most baffling aspect of the double-slit experiment is the role of the observer. If we try to observe which slit a photon goes through, for example by placing a detector at one of the slits, the interference pattern disappears. The act of observation seems to force the light to choose a path, collapsing the wave function and resulting in the two-band pattern we would expect from classical particles. This observer effect is one of the most debated aspects of quantum mechanics. It suggests that the act of observation doesn't merely record reality, it somehow participates in shaping it. The very presence of a conscious observer or even a measuring device seems to influence the outcome of the experiment. Section 6. Interpretations of quantum mechanics, making sense of the bizarre. The bizarre findings of the double-slit experiment have led to various interpretations of quantum mechanics, each attempting to explain the strange behavior of light and matter at the quantum level. The Copenhagen interpretation, one of the most widely accepted, suggests that particles exist in a superposition of states until measured, at which point their wave function collapses into a definite state. Other interpretations, such as the many worlds interpretation, propose even more radical ideas. This interpretation suggests that every quantum measurement causes the universe to split into multiple universes, each representing a different outcome of the measurement. Section 7. Modern applications, from theory to technology. Despite its seemingly esoteric nature, the double-slit experiment and the principles it embodies have had a profound impact on modern technology. The development of lasers, transistors, and even medical imaging techniques like MRI wouldn't be possible without our understanding of quantum mechanics. The experiment highlights the wave-particle duality of matter, a concept that is fundamental to our understanding of the universe at the smallest scales. This understanding has paved the way for numerous technological advancements that have revolutionized our world. Section 8. Quantum Computing, Harnessing the Power of Superposition. One of the most exciting applications of quantum mechanics is quantum computing. Unlike classical computers that store information as bits, which can be either 0 or 1, quantum computers use qubits. Qubits can exist in a superposition, simultaneously representing both 0 and 1. This unique property of qubits allows quantum computers to perform computations that are impossible for even the most powerful classical computers. They have the potential to revolutionize fields like medicine, materials science, and artificial intelligence by solving problems that are currently intractable. Section 9. Conclusion: The enduring mystery. The double-slit experiment, with its mind-boggling results, stands as a testament to the strangeness and wonder of the quantum world. It challenges our classical intuitions and forces us to confront the limits of our understanding of reality. The experiment's implications extend far beyond the laboratory, shaping our understanding of the universe and our place within it. While the interpretations of quantum mechanics may vary, the profound impact of the double-slit experiment is undeniable. It has opened our eyes to a reality that is far stranger and more wondrous than we could have ever imagined. A reality where light is both wave and particle, where observation shapes the observed, and where the very fabric of existence shimmers with uncertainty and possibility.